Hello to everyone who's watching on YouTube. We'll get started in, let's say, 10 minutes. I'm just waiting for a few people to join the session in person. So if no one joins, like after 10 minutes, I'll anyways start discussing. So we'll get started in like 10 minutes. Okay, so due to some technical issue, my camera is not working. So I'll just uh, I'll just be using my microphone for today. So hello. So I see that no one has joined the session in person, but like whatever. So hello to everyone who's watching on YouTube. I'm Lakshya Saggi, the problem solving TA for the NPTEL Games and Information course. And today we are having this session outside of our usual timings of Monday 6 to 8 p.m. because this is not a problem solving session, but this is more of a summary session. So this will be the last interaction I'll be having with you guys, at least for this semester. Yeah. So in this session, we won't be discussing any problems or anything, but rather just summarizing whatever we have done throughout the course. And by summarizing, I just mean like making you realize like how far we have come into the course and building a bigger picture around what we whatever we have discussed. So I don't think this session will be too long. It would probably be like a 40-45 minute session, and it will just be acting as a quick revision or reminder of were covered. Of course, I won't be going into all the definitions and everything which were discussed in the course because again, like that can't be done in like 45 minutes. So we'll just be discussing like the main things which were covered in the course, and probably like we'll be going over a high level idea of many concepts uh, rather than informing like what those concepts were in detail. So I again have a, a bunch of notes prepared for today. I'll just share my screen so that we can get started. So let me just share my screen, guys. Yeah. Okay. I hope my screen is visible to everyone. I'll just yeah. Uh, so let's just so in initial weeks, at least from like what I gather, a lot of the things which are covered in initial weeks were mostly the things which we were applying in the later weeks itself. So it's not like you guys need much revision about the initial weeks, the things covered in the initial weeks. So I've just listed out the main topics which were covered in the initial weeks to just act as a reminder of what things were covered. But I won't be going into much details. I will just be going into detail of some extra stuff which was covered, but mostly we'll be trying to summarize the latter weeks. And this is because in latter weeks there was much more theory involved and everything used like the concepts which we built over the initial weeks. So initial weeks were more of exercises, and the latter weeks are actually the ones which showed like the importance of this course or like importance of modeling games in different ways. So yeah, in the first week itself, we just discussed about what are dominating strategies and what are pure Nash equilibria. So what are the dominating strategies? So dominating strategy for I won't be writing this down, but dominating strategy for a player is just a strategy like uh, from which will be better for that player irrespective of whatever other players are playing. So for player I, whatever other players other than I play, if a strategy S is always giving better payoff for the player I, then that strategy is the dominating strategy for the player I. And then what's the pure Nash equilibria? Uh, a pure Nash equilibria is just like what described. So as over the set of pure strategies. So we'll be describing the term pure strategies because yeah, like there are mixed strategies and there are pure strategies. So over the set of like all pure strategies, if uh, if there exists a strategy profile, what's a strategy profile? A strategy profile is a set of strategies played by like players 1 to n, such that no player has any incentive to switch from that strategy profile to any other. Which means that if a player is playing some strategy S, if a player I is playing some strategy SI, then player I has no incentive to switch from SI to any other strategy, while assuming that others are still playing the same strategy which they were playing earlier. If this is true, then we call that the players are in a Nash equilibria. And the concept of Nash equilibria is important because it helps us model like real life situations. because all the players will want to arrive at such strategies such that no player has any incentive to switch. Because if any player has incentive to switch, then the player will indeed be switching, because every player is just greedy and wants to maximize or minimize his or her payoff. But we showed that actually this pure Nash equilibrium does not always exist. Like in a game of rock paper scissors, the pure Nash equilibrium never exists. So then we introduced a more powerful tool in week 3, which was like a mixed Nash equilibria. And what's a mixed Nash equilibria? Mixed Nash equilibria is where now the players are not just allowed to play like these deterministic strategies, but are allowed to play randomized strategies, which means like they can play with some probability, let's say with probability 1/3 a strategy A, with probability 1/3 strategy B, and with probability 1/3 strategy C. Suppose strategies A, B, C's are rock, paper, scissors respectively, then yeah, if the player plays like this, then you can actually show that the no player will have any incentive to change this probability distribution. And yeah, so that will be a mixed Nash equilibrium. Week 1, actually, we did not just discuss straight away this mixed Nash equilibrium, but in week 2, we first tried to model this, the concept of information in games. So note that this course is named Games and Information. So essentially, while the players are playing games, games are means of players having to maximize or minimize their payoffs. But we also need to understand that the information available to the players, like whether everyone knows everything or if someone doesn't, this kind of information also plays a very important role in uh, deciding the final outcomes of the game. So then we discuss what's the Orman's model of incomplete information, and this was quite simple, and we discussed some problems related to it. And then let's go back to what we are discussing. So yeah, in week 3, we introduced the concept of mixed Nash equilibria, and we also introduced the concept of zero-sum games. Zero-sum games are games where, like, if one player is, so these can be informally thought as if one player is winning, then the other player is definitely losing. So this means that the sum of utilities of all the players remains equal to 0. Or you can say that the utilities of players are negatively correlated. If one player's utility increases, other player's utility will decrease. So those were zero-sum games, and we actually showed that, like, okay, first we have introduced the concept of mixed Nash equilibria, but how do we even know that it exists? So actually, we showed that this mixed Nash equilibria uh, exists in zero-sum games, and this was shown over the course of week 3 and week 4, over the lectures of week 3 and week 4, where we introduce first the concept of saddle points in games, and then the security levels. Security levels are nothing but the minimum utility which a player would want out of a game. And then there was this one Newman's min-max theorem, which just says that uh, minimum over set of maximums is greater than equal to maximum over minimum. Or I don't like to call it this way. Like I don't like to think of it this way, but rather this is just saying that von Neumann's min-max theorem just says that in a linear program, the optimal value of a primal program is actually equal to optimal value of a dual program, or it's at least always greater than equal to optimal value of dual program. It can be equal in many cases, but sometimes like it might be that primal and dual like don't even exist or something. So okay, let's just not discuss that, but rather this can be modeled as just saying that so let's say primalism. So in linear programming, let's say the primal program is a minimizing program. Then the dual will be a maximizing program. And you can always say that the optimal value of the primal program will be greater than equal to optimal value of the dual program. And under some conditions, like these values will also actually be equal. So yeah. And the linear program for calculating like the minimum security level, we modeled it as like this kind of a thing where we just said that okay, we want to maximize the, for a player I, we want to maximize the security, like we want to find out the maximum possible security level for that player. And then we just introduce the constraints so that this could happen. And yeah, this was the linear program for calculating the uh, minimum security level. And we want note that we want to maximize this minimum security level. So that's why I'm saying like this is kind of a max min kind of a thing, that we want to maximize this, but actually this is a minimum. So W is something like a minimum, and that's why everything like AZ denotes like uh, Z is the strategy and A is the payoff matrix. So say AZ should be greater than equal to this uh, this W. Like effectively, what this means is like uh, like over like over all these all the rows of A, we have to find such a Z such that AZ will always be greater than equal to W. So like W is actually minimum possible payoff. So what we are doing is we this constraint imposes that W is a minimum possible payoff, and we are kind of maximizing this payoff. And this was what this primal LP denoted. This is actually a dual LP, and like the primal LP was just so this finds max min, and its dual, which will actually be the primal, will just find min max. So if you take the dual of this linear program, you will just arrive at this program, and this will find the min max for you. And this is like dual of a dual is anyways primal. So yeah, so this is a primal linear program which calculates the min max, and this calculates the max min. And one dimensional maximum says that this always remains greater than this objective value. The optimal value here remains greater than equal to this, and like under some conditions, like actually these two are equal. And this is what helps us calculate like this equality is precisely what helps us calculate Nash equilibria in zero sum games. So, and this is because like since we are talking about zero sum games, if one player is minimizing, other player is naturally maximizing. And so if we are calculating like so one thing, so one linear program, the primal linear program will correspond to, let's say, the minimizing player, whereas the dual linear program will correspond to the maximizing player. And you can actually see that like if primal objective value is equal to dual objective value, then these players will indeed arrive at a common strategy, where like a common strategy profile where both the players, if they play their specific randomized strategies in these strategy profiles, then they will indeed have like equal payoffs and no one will want to deviate. So this was what we saw. So effectively in week 4, we saw how one can show the existence of Nash equilibrium in zero sum games. And then obviously like zero sum games are relaxations of general games. In general games, you necessarily don't have that like payoffs are negatively correlated for the players. So it might be possible that in general games, if one player is gaining, then the other player is also gaining something. So the sum of the utilities is not necessarily zero. So then in week 5, we showed that we talked about these non-zero sum games, or which can be thought of as general. These are general games. So in general games, so in week 4, we saw that mixed Nash equilibrium actually exists for zero sum games. But does it exist for general games also? That's a interesting question, because if it exists, then it's a very powerful tool, right, to solve games and everything. So here we actually use some fixed point theorems like Kakutani's fixed point theorem, which actually helped us to prove existence of Nash equilibrium of a non-zero sum game in a finite strategy space. So here we use this Kakutani's fixed point theorem, which was, and the argument here on a very high level was something like for any strategy, let phi of s be the best response to that strategy profile by some, like for a player I, if all other players are playing some strategy profile, let's say X, then let phi of X be the best response by the player I to the strategy profile X of the other players. And then you can model this as a function between the sets. And uh, actually, after that, you can show some properties of the sets, which actually prove using like fixed points that so basically, a fixed point is a point where phi of x will be equal to x. So actually, you show that there exists a point in the space where phi of x actually, like where the set of best responses is actually equal to the response itself, which all the players are giving. So the set of best response given by the players is actually the best response which the players are, which is actually equal to the response which the players are already playing. So if best response is actually equal to the response you are already playing, then you are actually in a Nash equilibria setting, right? Because then if everyone is playing their best response, then no one wants to switch. And this is essentially how you try to use Kakutani's fixed point theorem to prove existence of Nash equilibria. So you model this best response as a function, and you show that this function between sets has a fixed point. But this only talked about like the setting where we only had a finite pure strategy space, that the set of pure strategies was finite. But what if the set of pure strategies was infinite itself? Suppose the set of pure strategies was itself a real number between 0 and 1. A player can play any number between 0 and 1, and that will be considered a strategy for the player. So then we actually showed that a Nash equilibria exists even for infinite pure strategy space. Suppose if every player has the strategy space of, like, let's say real numbers from 0 to 1, then a Nash equilibria exists here also. And here there is a very interesting property of Nash equilibria. Here there exists a Nash equilibria even if every player plays only some pure strategy. So in a finite strategy space, we initially discussed that a Nash equilibria does not necessarily exist, like in a game of rock, paper, scissors. And that's why we introduced this mixed strategy, mixed Nash equilibria, and we showed that in a mixed Nash equilibria always exists. But if we are just restricting ourselves to infinite strategy spaces, then actually Nash equilibria always exists, even in the case of, even if we just consider pure Nash equilibria. So even without using randomization, a Nash equilibria will exist. And how did we prove this? This was done using Brouwer's fixed point theorem. And like this was used to prove the existence of Nash equilibria in infinite strategy space. So again, like usually these existence results require like kind of like some kind of a fixed point argument, and here also the high level argument was kind of this only, like you choose a function of best response and you show that this function has a fixed point, which means that the best response is the response you are currently playing. So yeah, if your response is the best response anyways, then no one will have an incentive to switch from that. So these were essentially like this week 5 was a bit involved, I guess, but I think the high level idea, the you should obviously like revise these lectures, but the key high level idea of techniques which were used here was this, which I just said that first of all, you try to model the best response as a function, and then you try to show that this function will have a fixed point using these kinds of fixed point theorems. And as soon as you do that, you're done. So, okay. And then after showing all of this, then we came into week 6, where we started discussing about simultaneous games. So simultaneous games are okay. Like simultaneous games is not a new concept. Simultaneous games is just a game where maybe I should try it. Yeah, dynamic games. So in simultaneous games are games like which we are discussing till now, that simultaneous games are where all the players are playing simultaneously. Like players are not playing turn by turn, but are rather playing at the same time. So the simultaneous games don't have the notion of time, like everyone is playing together, and then the output of the game is decided. Whereas dynamic games are games where like there can be a notion of time, like that at t equal to 1 player A plays, then at t equal to 2 player B plays, and so on. So yeah, so we saw the difference between the simultaneous games and dynamic games, and we tried to then in week 7, okay. Okay, and then Okay, and then we talked about these like dynamic games. Like okay, so if the players are playing turn by turn, then how can you actually model these games? So dynamic games can be modeled in extensive form games, which we'll describe later. But they can also be, so note that dynamic games can also be modeled as normal form games. And what are like games in their normal form? It's just a game where like which just consists of a payoff matrix for each player. So like so we talked about this till now also that uh, like uh, till week 5 we only discussed about the simultaneous games where all the players are playing together, but in dynamic games players can play different at different times different things. But note that even though players are playing different things at different times, the strategy which the player has in mind, that if a player plays this at time equal to 1, I will play this at time equal to 2. So even though the actions are decided at different times, the strategy which the player is actually going to play is decided by the player at the start itself, before the game starts. And why is this the case? Because if before the game is starting, the player will have in mind that if the player, so player A will have in mind that if player B is playing something, then I will, like if player B is playing, let's say scissors, then I will be playing heads. Like if you are modeling rock paper scissors, let's say if rock paper scissors is a dynamic game, then if the player going first plays a rock, then the player going second will definitely play a paper so that he can win. So even though the actions taken are dynamic, they can change with time with respect to what the other player plays. The set of strategies, like the strategy which the players will think they are going to play to maximize their utilities at the end, these strategies will actually be fixed before the game even starts. So even though dynamic games are games where actions are played over time, these can be thought of as dynamic games can also be thought of as simultaneous games in the strategy space. So if you model strategies can be modeled as functions of like actions taken by the other player. So you have to choose one function out of many possible functions. So that is your strategy. So effectively, we saw that dynamic games can actually be modeled as normal form games also, or like simultaneous games in the strategy space. And simultaneous games we know have a and we can draw like a payoff matrix, like which we did earlier also. Like we can draw payoff matrices for these simultaneous games and see like what kind of an equilibrium will exist or will not exist. And usually when these dynamic games are represented in their payoff matrix form by representing all the strategies as like their strategy space as the possible action taken by the player, then these games are referred to as being in their normal form. So these are effectively the same. So one can model a game as in an extensive form game extensive form game is a game tree where which we have been discussing for a long time, but I'll just define it again. But if extensive form game is just a game in their actual game tree form, which actually shows the flow of the game, like at what point what player is playing and at what point what player is not playing. Whereas normal form game doesn't actually show you the game tree, but it just shows you the final payoff matrix. That if a player decides to play some strategy, what will be the payoff for that player? So even though these games might look different, but the same dynamic game can be modeled in both of these forms. Usually, normal form games are useful for us if we want to find all possible Nash equilibria of the game. Then normal form games are useful. Otherwise, we just want to succinctly represent a game. Because in normal form games, the set of strategies can go into exponentially, like grows exponentially. The set of strategies grows exponentially. Whereas like extensive form games are just trees, and so they provide a succinct representation of the game. So as these grow exponentially, they also have like more information and are more useful for us. But we try to use these in real life because they provide a far more succinct representation, and a lot of cool things can be done when games are represented in their extensive form as well. So maybe just defining what is an extensive form again. So extensive form game, a game in its extensive form is just a game tree where a specific vertex indicates the starting point, a cause for each player at each leaf node. So it's a tree, so tree will have a root, and also tree will have leaves. So each leaf represents the utilities. So each leaf represents an outcome of the game, and at an outcome you have to describe what is the payoff that every player gets. So there is a root node which indicates the starting point. There are these outcome nodes which are leaves, and the nodes of the tree, except these leaf nodes, uh, divide are actually nodes representing players. Like at what so if a node, so different nodes correspond. Like if a node is labeled, let's say one, then that means that player one is going to play when it is at that node. So every node corresponds to like a player's turn, like what player is going to play. And then the possible outgoing edges out of that node represents the possible set of possible actions for that player. And then we also introduce the concept of information sets. Like this induces like the role of information into the game. Like these information sets are similar to what we described in Orman's model of incomplete information. Here, like if two nodes are in the same information set, then it means that a player who's like the same player who's taking actions at these two possible nodes cannot distinguish between these two nodes, which essentially means that like the player has some less information than, like if the player does not have complete information. If a player has complete information, a player can actually always know at what state is the game in. Whereas, like suppose if a player has like two nodes in the same information set, then that means the player does not have complete information about the game, because it cannot tell at what state of the is the game exactly in at present. And so this can result in like some inefficiencies for the players. So partial information can result in some inefficiencies. And yeah, so extensive form games in the extensive form are quite cool. They can model this information also and all the actions also. So these are what you call usually extensive form games. And then these dynamic games, like these dynamic games are the games like which you just described. So in which players are playing over time. So then a natural question arises like, okay, one way to find out a Nash equilibria, or like what will these games end up in? Like whatever these games end up in is called the equilibrium. So usually simultaneous games ends up at some point of Nash equilibria, because at that point no player wants to switch from their current strategy. Whereas like one needs to also like, but finding out like Nash equilibria using these normal forms is quite expensive, as I already told that these can be exponentially large. Like games when represented in normal forms can be exponentially large. So we try to find out the equilibrium in dynamic games. So one way is definitely using normal forms, but one can also try to find out equilibrium in dynamic games using extensive forms. So yeah. So one of the equilibrium which we discussed, like which one naturally tends to find, is an equilibrium which can be found out by backward induction. So there can be an equilibrium where like it's a DP like thing where you find out equilibrium for the leaf nodes, and then you go one level up and try to find out the equilibrium of the uh, red node when we know the equilibriums of these leaf nodes, and then you go one level up further. So this is how you are doing backward induction. Like you are going levels by levels and levels. So when you arrive at this node, if you already know the equilibriums of blue and red node, then you can find out actually what's the best possible action to be taken at this red node, at this root node. So note that this is not the only form of equilibria in which this game can end in, but this is one equilibria in which this game can end, and this is called like uh, the induction obtained using uh, uh, the equilibrium obtained using backward induction. As already discussed, like to find all possible equilibria, one has to go to normal form. But if one is just interested in one equilibria, then you can actually find it using these backward induction kind of arguments. But there can exist other kinds of equilibrium also, uh, like I already told you about these. Okay, we discussed this in lectures also, like thread equilibriums and things like that, and also like one more property was that a dynamic game inherits equilibrium from informationally inferior games also. So what are informationally inferior games? Informationally inferior games are the games where players have strictly less information than they have in the actual game. And then if you model these information inferior games, then their equilibriums will also be the equilibrium in the actual games. And yeah, this was the proof for this was also discussed in the lectures and everything. So this was an important property that to find out further equilibriums of dynamic games, one can try to find out equilibriums of informationally inferior game, and then try to find out the final equilibrium for the game. And then there were various concepts like extensive, like further extensions of extensive form games. Like suppose one wants to find equilibrium in these extensive form games. So there was some relaxation, like one cannot always hope to find like equilibria efficiently in these extensive form games. But if there are some relaxations, like if it is of the form nested extensive form game or ladder nested, or is it's yeah. So we discussed that what's the nested extensive form game, and then what's the ladder nested, and then we described how to find out the equilibrium in a ladder nested single act game. And then we describe what are stage-wise multi-act games and what are these games in their feedback form, and how do we find this feedback match equilibrium. So note that even though these are many terms, but the high-level idea is like the core objective everywhere is just to find any possible equilibrium of the game. So everything can be done by using normal form, but normal forms are very expensive to make. They're exponentially large. So one tries to find out suitable relaxations of these dynamic games where even using extensive forms you can try to find out equilibria. And like this ladder nested single act games is a relaxation of the actual game. Like every game might not be in ladder nested single act form, but the games which are indeed in this form can have a further efficient algorithm to find an equilibrium. And this is the algorithm which we discussed in the lectures, and then we talked about stage-wise multi-act games and what is feedback match equilibrium. Okay, then. So then in week 9, uh, we discussed this mixed strategies. So basically, we discussed what's about randomization in a dynamic game. So previously we only discussed about like these in dynamic games, like these uh, like we are only discussing pure strategies, but one can also model mixed strategies in these dynamic games. So, but note that uh, how do you do randomization in a dynamic game can also differ. Like there can be a uh, one way, like how we described pure strategies previously, like how we described a mixed strategy previously was how do you randomize? You choose a pure strategy at random from a probability distribution, and this is what you call a mixed strategy. So in game, first put the game in its normal form, then you have many strategies, then just choose one strategy at random according to a probability distribution. So that's what you call a mixed strategy. But another way can be that at every point of the game, whenever a player actually arrives at some point in the game, at that point itself the player decides to do randomization. So in like mixed strategies, the randomization step is done at the start itself. As soon as the game starts, the randomization is done, because every player chooses one pure strategy at random and abides by that strategy throughout the game. Whereas in this behavioral strategy, everything is not initialized at the start. So as the game moves along, the player starts to randomize. So P1 will randomize between these and this as it's P1's turn. Then P2 will start randomizing as soon as P2 arrives here and it's P2's turn, and so on. And P1 will randomize here again. So it's not like what steps they are doing will be decided at the start itself, but it will be decided as the game goes along. And this is called behavioral strategy. And actually, what we also showed was these mixed strategies and behavioral strategies are not the same. Like, and we showed an example also that in this kind of a setting, behavioral strategy is characterized by two parameters, whereas a big strategy is characterized by three parameters. So these are definitely not the same, like since their parameters are even not matching. And then we also showed, and then it was discussed that, like, what do you mean by equivalence of strategy? So equivalence of strategy just means that, like, if a strategy, like if a mixed strategy can be simulated by a behavioral strategy, or if a behavioral strategy can be simulated by a mixed strategy. But it was shown that mixed strategies and behavioral strategies are not equivalent in general. So an example for this was also discussed. But note that behavioral strategies are strategies which are kind of useful for us, because for finding out mixed strategies, one has to initially form, like convert the game into its normal form, find out all the pure strategies which can be exponentially large in number, and then uh, try to find some kind of a strategy, like some kind of probability distribution over these pure strategies. Whereas behavioral strategies are quite simple, like as you just go along, you do some randomization. So we would want that like mixed strategies help us to find out the Nash equilibria actually, but can we try to use behavioral strategies to find out Nash equilibria also? And then this was discussed that like there were some conditions of perfect recall, like, and what are the conditions of perfect recall? Like I won't go into the formal definition, but the informal definition was if a player, like basically no player forgets anything. If the game is such that no player forgets anything, basically means the player cannot forget the actions that he took. A player cannot forget that he took an action at all, and a player cannot forget what he knew. So if these properties are satisfied, then we come to what's called the Kunz theorem, which says that every mixed strategy has an equivalent behavioral strategy. So if a game has perfect recall, then actually you can assume that mixed strategies and behavioral strategies are equivalent. So instead of going the route of mixed strategies, we can try to simulate behavioral strategies, which are easier for us to do because they are much more simpler. But yeah. So again, what we are doing is, so the high level idea for this course is we are always looking at trying to find out the equilibrium of the game, and we are trying to do it in a most simplest manner possible. As we saw, like finding out, first of all, we come to know about this existence of equilibrium via mixed strategies, but then we know that mixed strategies are kind of bad for us. So can we do away with mixed strategies and choose behavioral strategies instead? And we showed that yeah, indeed it can be done. And this was Kunserum. And then in week 10 we described games of like imperfect equilibria and what Stackelberg equilibrium is. So now we did away with the concept of Nash equilibria and everything, and we turned to some further kinds of equilibria in games, like under different settings of the game. So the most general kind of equilibria is Nash equilibria only in like simultaneous games, in dynamic games, and everything. But as you change some settings of the game, like you can talk about further different equilibria, and like yeah, and we turn to these different kinds of equilibria, which were like in games of imperfect equilibria and Stackelberg equilibrium. Like Stackelberg equilibrium was like, if you remember, a leader-follower equilibrium. Like leaders play something and followers then have to play something among themselves. So followers themselves among themselves are in Nash equilibria, but not with not in equilibria with leader or something like that. And then in week 11, like this is quite recent, so maybe I should not go over it in so much detail. Yeah, okay. And then we discuss, okay, like in starting week 11, we started to discuss like, okay, maybe what's the role of community? Like, okay, till now what we have done is we have tried to model games using knowledge, using information and actions and utilities and everything. But still, every player is taking an action on his or her own. There is no communication going on between the players. So then we tried in week 11 to see what happens to the equilibriums of the game if we allow for some communication, not between the games, but before the game starts, which is called pre-play communication. So if some pre-play communication is allowed, if we allow some pre-play communication, then these kinds of games, sender receiver games, and communication as part of gameplay can be thought of as every player can be taking an action or can be doing a signal. So these are sender receiver games. And then we talked about this principal agent contract theory, which is just saying that uh, like which basically discuss about wages, like different cases of wages between like an employer and an employee. So basically, here we saw that what employer knows about the employee, like, or the level of granularity at which the employer knows about the employee, like what kind of work he's doing, is he doing any work at all or anything, affects the wages of the employee. So the information which the employer has about the employee actually affects the wages of the employee in the equilibrium. Like we saw that uh, there can be cases where a moral hazard arises, where like actually employer has to give employee certain wage even if employee does not work at all. So so here the moral hazard is in terms of employee, that uh, like employee will be paid a minimum amount even if employee does not choose to do any work. And in this kind of a setting, like it's a moral hazard for employee, like if he's getting paid without even getting, like, without even having to work, then does he work at all? It's up to morals of the employee, something like that. And then we discuss the role of nature action. So basically, so uh, usually, as you may see, like some people seem to be lucky or like something like that. So some person at work might be lucky that something works out for them, whereas another person who might be more hardworking or more talented than some person than the first person might get unlucky, and due to that might have worse outcome than the first person. So these kinds of action can be modeled. This luck can be modeled as like nature taking some kind of action, or nature having a probability distribution and making an instantiation, like a probability distribution over the luck of the players. And yeah, so then there were different cases discussed, like moral hazards with hidden actions, and these cases were different because in these cases, like nature acts at different points of time. Sometimes like nature acts after the contract is signed and actions are taken. Sometimes nature acts before the actions are taken, but after contracts are signed. Sometimes nature acts before the contracts are even signed. And these are called like different things. And then we talked about signaling, screening, and then we tried to model moral hazards. And then we talked about like micromanagement, like uh, yeah, that and we actually showed that like basically what is micromanagement. Micromanagement is nothing but what the employer uh, uh, actually uh, expects out of employee, the output that employer expects out of employee, but employee is actually not doing it for employer's sake. The employee is doing it for wages sake. So if an employee is getting the same wage but for doing lesser amount of work, then employee probably won't be doing more amount of work, but employer wants the employee to work more. But and that's where this cost of micromanagement comes in. Like if that employer wants to the employee to work more, but employee only for wants to maximize his or her wage, and so like the difference in the work output corresponds to the cost of micromanagement for the employer. Like employer's cost actually could be more if employee worked harder, but employee only works not to make employer happy, but rather to earn wages from the employer. So yeah, then we modeled this and we talked about this information rent and yeah, cost of micromanagement. And in the last week, yesterday in the yesterday's session, we talked about like different set. Again, we talked about this role of pre-play communication. Like, so we in week 11 we also talked about what are binding contracts and everything. Like, suppose like in this pre-play communication, suppose players sign some contracts, they have to bind by it. Like they are forcefully bound by the contract if they sign it. Then how does it affect the gameplay? And then like making these like making the players bind to these contracts is a very expensive operation for us. Like you can't always ensure that the players will always bind by the abide by the contract that they have signed. So then one talks about like non-binding contracts. Like okay, like, we saw that payoffs achievable communication and binding contracts is a very large set, so you can achieve uh, a large types of payoffs if you are using pre-play communication along with binding contracts. But we also saw that even if we are using non-binding contracts, that if the player signs the contract, even then like they can choose to do away from the contract, or like yeah, walk away from the contract. So one might think like, what's even the use of non-binding contracts? One might not even have the contracts at all if one is not making these contracts binding. But even these non-binding contracts actually are a much stronger model for us than just modeling the games via Nash equilibria. And why is this the case? Like it actually happens that payoffs achievable under non-binding contracts is a superset of payoffs achievable without replay, like without using any contracts at all. And this intuitively, this is because even though the contracts are non-binding, these contracts allow us to have some pre-play communication between the players. So previously in Nash equilibrium, every player was acting independently, and but now even though players are can be non-binding contract, but they are communicating with each other. So what this ensures is that there is kind of a, like now these players can share some random variables. Like right now, like their randomization, like in Nash equilibria, their randomization was independent of each other. But now they can have some correlated random variables if they're allowed to communicate, and this allows for and this is the high level intuition of why players can now achieve further more kinds of payoffs. And here also it can be modeled as direct communication and indirect communication. Indirect communication is the communication with a mediator, and this is even a strict superset of direct communication, because now in indirect communication, like a mediator can hide some information from the players, where in direct communication every player has exactly the same, like all the information. So yeah, you can actually achieve further new kinds of payoffs with indirect communication, which you also saw yesterday in an example. And yeah, like obviously, this indirect information is very much useful to us, like this part, because this is what usually happens in real world scenarios also. Like there are stock market advisors, real estate advisors, real estate brokers, or like Google Maps, which advise us, which are like mediators for us, which advise us to take some route or to buy some property or something. But they don't tell us what have they told to other people in the area. They might be giving different advices to everyone, but this helps us. This helps actually to achieve like further new kinds of payoffs in the world, like where everyone may be better. And note that the best model, the strongest and the best model for everyone is this the model with binding contracts. But yeah, the model like binding contracts is a very, like in real world it's like usually abided by the law. Like when you are like signing a letter like related to law or something, then like an order by the court is binding. But Google Maps suggesting you a route is non-binding. Like you can ignore the decision taken by Google Maps, like ignore the advice given by the Google Maps. So this non-binding contract can be indirectly thought of as advice, whereas binding contracts are actually law. So the payouts achievable under law are furthermore like you can just always have some kind of a law so that everyone has to do something, whereas in advice, like everyone is still free to do something on their own. So this binding contracts can actually achieve further more kinds of things than non-binding contracts. But these are very expensive to do. So like this is also a good model, like payoffs achievable with indirect communication. And then we talked about correlated equilibrium, like what kind of equilibrium do these games achieve? And here we saw about like there exists some equilibria, and for these equilibria to exist, like everyone should have an incentive to listen. So basically, there always exists like a mediation strategy by the mediator, so that everyone will actually be listening to the mediator, because like everyone will be better off listening to the mediator rather than not listening. And this can be modeled again as like payoff for every person, since everyone in the end wants to maximize payoffs. Payoff for every person while listening to the mediator is greater than when the person doesn't listen to the mediator. And this is kind of an incentive for the person to follow the mediator or like be obedient to the mediator. So if the strategy of the mediator uh, has this property that the payoffs following that strategy is greater than equal to payoff not following that strategy, then this is what is called like incentive compatibility or obedience constraints. And a strategy by the mediator the advice by the mediator which satisfies these incentive compatibility constraint helps us arrive at an equilibrium, which is called correlated equilibrium. And a correlated equilibrium, you can show that always exists. So always, but like it's computationally might be hard to compute. So that's why mediation is also a challenge. Like find, like we always know that strategy by the mediator will exist, which will be good for everyone. But like actually computing and finding out that strategy might be difficult. And that's where like ingenuity of these Google Maps and like all these advisors comes in, because there is no fixed formula for giving the, like there is no fixed algorithm or efficient algorithm to find out the perfect advice. But they can have their approximate algorithms, some advices which are approximately perfect or something. And yeah, and this is where like the level or the intelligence of the mediator comes into play. Like how good is the mediator is dependent on what kind of advice they give. And then we talked about Bayesian games with mediated communication, which is nothing but again, like we discussed this yesterday only, but this is again a type of like this can be modeled as something like correlative equilibrium itself. And yeah, so in the end, we discuss about something like a revelation principle, which just says that any communication system where players are communicating with each other, its equilibrium can be modeled as like correlated equilibriums also. So even though there does not exist a mediator and everyone is talking to each other, so this kind of thing is very difficult to model. But actually, like this revelation principle actually shows that you can actually like do away with all these complexities in the problem and just think that a mediator is existing, which is mediating between all the players, and then you just have to find a correlated equilibrium in this game, and which is something like which is also like not computationally easy to compute, but a lot of, but this simplifies the model at least which we are working in. That's why like that's the beauty of this revelation principle. So yeah, so I guess yeah, like this covers I think more or less. So we did not discuss much things in detail. I just like wanted to give you a high level idea of what we are doing. So essentially what we are doing is we are always trying to model games and how the player, how information and communication affects those games. So yeah, and that's how like so we started out with the simplest kinds of models, but maybe we were not satisfied with the simplest kinds of models. We wanted to do something more or like achieve some more kinds of payoff, and so we introduced further new concepts. And we also wanted to be computationally efficient. We just are not okay with existence result, but we want to compute also. So we saw how in there are some relaxations in which we can actually compute also. And yeah, so one might think like some of these results may be redundant, that okay, if Nash equilibrium exists, then like we are done. Like every game has a Nash equilibrium, we don't need to do anything else. But see that this pre-play communication and everything allows us to do something more than Nash equilibrium. And even if we are just in the domain of Nash equilibrium, like modeling this Nash equilibrium in different forms can find help us find like equilibria in a more efficient manner rather than that exponential time manner. So we want to do everything not in exponential time, but efficiently in real world. So these kinds of models help us to do things in efficiently. So something like that. So okay, then I guess this more or less covers the gist of the whole course. So I hope you guys appreciated the course content and like why is modeling these games and the role of information and communication important, because this is actually what happens in real world also. So yeah, so I guess this was it from my side, guys. Since no one is in the session in person, I guess I'll just close the session now. So once again, like for the last time in the semester, thanks everyone for watching this session. So I'll hopefully see you guys in the next semester in some other course also. But yeah, till then, uh, goodbye, guys. I'll be closing the session.